This slide talks about ALU control. So ALU used for load store, the function is we perform add operation. In case of load, we perform add operation to generate the address. Similarly for store, we perform the add operation for generating the address. For load, we generate the address for performing a read operation, and for store, we perform the write operation on that address. For branch, the function is subtract. How? So branching is decided based on the output of the ALU. So subtraction is performed here. For example, if the value of the two registers are subtracted, it could be 0 or it could be anything other than 0. So when the value is 0, then the branch equal to condition can be satisfied, and when the value not equal to 0, then branch not equal to condition can be satisfied. For archetype instruction, function depends on the function field, because we know in archetype instruction we may have add, sub, we may have a SLL and all other instructions. So for archetype instruction, we all know that the opcode is all 0 and function field determines which instruction it is. So ALU control, when it counts from when it exits from the control unit, then it generates these 4 bits of control, and these 4 bits of control goes to the this this 4 bit of control comes from the ALU control unit to the ALU that decides which operation to perform. For example, if all the 4 bits are 0, then the operation is AND. If it is 1, then it is OR. If it is 2, then add. If it is 6, then subtract. 7, then set on less than. And if it is 12, then it is NOR operation. Or in other words, 1100, it's NOR operation. Here we could see the ALU opcode that is generated by the control unit, and based on this value from the control unit, or these control signals from the control units, ALU function gets generated that goes to the ALU for performing specific operations. If we look here, then the main control unit, or so this is the instruction type, basically the arc type instruction, load store type instruction, and branch type instruction. Load store and branch, they are I type instruction. So we already know the name of various field. For arc type instruction, this is our opcode. In fact, for all these 3 instructions, this is opcode, this is opcode, this is opcode. Now, for archetype instruction, we all know that opcode will be 0. That's why it is 0. And then we have RS, RT, RD. That means source 1, source 2, and destination. Then shift amount and function. So this bit this value tells the bit which bits are assigned for opcode, which one for which bits are assigned for RS, and so on. As it can be seen that bit 31 to 26 are assigned for opcode, 25 to 21 RS, and for example 5 to 0 are for function. Similarly, for load store, it's 31 to 26 for opcode, and for load the opcode value is 35, and for store the opcode value is 43. Then we have RS, RT, and then the address. For branch, we have the branch opcode is 4, and then we have RS, RT, and the address. This is the data path with the control unit. So this is our control unit, and as you can see, this control unit generates control signals for different components. For example, this is our register file. So this is the control signal for the register file. This one is called register write. So when we perform write back operation, this control signal needs to be enabled. Then ALU source, for this multiplexer, what it does is which input should it exit for the ALU. This signal decides that. So for example, when we are performing add operation, then port 0 will be enabled, and when we are performing add I operation, port 1 would be enabled. And then we have a memory write. So this signal will be enabled when we are performing store operation. And then ALU opcode. This is going to be 2-bit signal, and this goes to the ALU control, and this control based on the 2-bit signals, it generates 4-bit control for the ALU. And then memory to register. This is for write back operation. When we are performing add operation or archetype operation, then 0 will be enabled. And when we are performing load, then port 1 will be enabled. And then memory read. This signal will be enabled, or this link will carry the enable signal when we are performing memory read operations. So when we are executing load instruction, this signal will be enabled. And then this is for branch instruction execution, and then register destination are this. So these are the control signal that are generated by the control unit. Now, for archetype instruction, as we have discussed previously, that it is always a good decision to generate or design a generalized circuit where just by changing the control signal, we could enable different components, but the same circuit can be used to execute different instructions. Now, here, for example, we have archetype instruction. Archetype instruction. Now we could see here that some of the components are really light. So these are the components that are not used for executing archetype instruction. For executing archetype instruction, we need selection of 3 registers inside the register file. So this is going to select the source 1, this is going to select the source 2, and this one will select the destination. See, this is register destination. This one will be enabled. So port 1 will be enabled in case of archetype instruction. So this one will be enabled for selecting the destination. Now, in case of, let's say, we are executing add. So if we execute add, then let's write add instruction here. Let's write add here 10, 11, and 12. So if we write them, then this one select this port. So this one will select this port. So this link will select register 10 as destination, and this one will select register 11, and this one will select register 12 for two sources. And ALU in this multiplexer, this port will be selected because this link will carry data coming from register 11, and this link will carry data coming from register 12. So you perform the arithmetic operation, and ALU OP would send ALU control the 2-bit signal, and based on that it would generate 4-bit signal that would let the ALU know that it needs to perform addition operation of the value that is coming from register 11 and 12. After performing the addition, this link this link will carry the additional result, and it will end up in this multiplexer. But remember, this multiplexer have one input coming from this link, and the other one is coming from this link. So so the control unit through this link will send which one to select. In case of add, this one will get selected, and write back will be performed because this link will carry data for register 10. So this is how add operation will be, or add instruction will be executed. And as we can see that this component, then this component and memory element, they are not utilized here at all, but they are in the data path. Since we did not generate any control unit for these components, so they will have no role to play in execution of archetype instruction. Load instruction. So let's write a load instruction here. Load, let's say register 10 is the destination, 40 and register 11 is our base address. So this is our this is our load instruction. So how can we execute load instruction? If you look carefully, then you would see that this part is not enabled because this part is used for calculating branch address. This part is used for calculating, let's say, VA or VEQ. These are the branch instructions that we have. So this part will be required for calculating branch address. So load is not a branch instruction, so we do not need this part. But see, the memory unit is active now. In R-type instruction, it was inactive, but now for load instruction, memory unit is active. So when we are performing load instruction, ALU generates the memory address. This is not generating any data. That's why see this link. This link is not active right now. Even though this link is not active in the sense that logically this link is not active, but physically this is carrying some data, and that data is going to this port. But through this link, control is sending signal that would only allow data coming through this port to get to the register file. So if you look carefully, that in load instruction, we already have discussed that load instruction, we need program counter, then we need instruction memory, we need register file, we need ALU, and we need a data memory. See, in executing load instruction, program counter is active, instruction memory is active, register file is active, ALU is active, and data memory is active. So these are the components that we are using for executing load instruction. And if you follow the path for for the load instruction that I've just written, destination 10, 40, and base address 11. So this link, will select register 10. This would be the source. Sorry, this is this link will select a source register 11, and through this link it will select register 10 for destination. See, this port will be selected through the signal coming from this link. Okay, and this is how load instruction will get executed over the same data path which we use for executing R-type instruction. This slide shows the execution of branch on equal instruction, or in other words, branch instruction. If we look carefully, then we would see that in this instruction, or in this data path for this instruction, data memory part is not active, it's inactive. Similarly, this link is inactive because they are not required for executing branch instruction. But if you look carefully, this part is active now, which was inactive in case of R-type instruction. So this part is active now. Now, if we consider any instruction that is any branch instruction, or the instruction that is mentioned here, let's say branch equal to B E Q, let's say 10, 11, and else. So the ALU would check the value of register 10 and register 11, and the else, which is our branch point where the pointer would end up. We need to, this is 16-bit value. We all know that this is going to be 16-bit value because branch is I-type instruction, and this is going to be 16-bit value. For this 16-bit value, since this is going to be this is going to generate memory address, so this needs to be converted into into 32-bit, obviously sign extended, and left shifted by 2 just to make it word aligned. So this link will carry the 16-bit value, this one. It goes to the sign extension hardware, you generate 32-bit value, and that is shifted, left shifted by 2. So this link will uh, carry the branch offset value, which is 32-bit, sign extended and left shifted by 2. Now this link, that means this link would carry PC plus 4. Okay, this multiplexer has the option to select this one and to select this one. If it is branch equal to, that means the program needs to take a branch, then it would select PC plus 4 plus branch offset, this one, which means this one, this port. But if it is sequential execution, then it will select this one. So the link that is going to the program counter, or that is replacing the previous value of program counter, can have PC plus 4 plus branch offset, or PC plus 4 in case of sequential execution. Control unit through this AND gate selects which one should go to the program counter. Also, as I said previously, that data memory part is inactive here, which means memory write, there will be no enable signal. Memory to register, there is no write back, so you will have no signal here. Memory read, there is no memory read there, operation taking place, so this signal, there will be no signal here, no signal in this link, and no signal in this link. And ALU source, this link will select both the links coming out from the register file, since this is register 10 and register 11. So both these are inside the register file. So register ALU source would select port 0 of the port 0 of the multiplexer. That means this port will be selected, and you already have value coming from this link. So this is how branch on equal instruction would get executed. So in the if I explain it bit further, then ALU, we have this link coming from the ALU operation, and this would tell the ALU control to execute subtraction operation. How would the system would know that whether the branch equal instruction would get executed or not? After comparing the value that is inside register 10 and inside register 11. If they are equal, then this link would generate 1, and this is branch instruction. So the branch instruction, this link would also generate 1. So this link would generate 1, and this link would also generate 1. So if just let me erase this one. Now this link would generate 1. This link would generate 1, and you have, through branch control, you have 1. So this is 1, and port 1 gets selected. This is how branch on equal instruction gets executed. We shall be implementing jump instruction here. But before implementing jump instruction, let's review what is a jump instruction and how it works. So we all know that jump instruction, it has 6 bits of opcode, and then as it is given here, the opcode is 2 for jump, and then we have 26 bit of address. Again, we need to make this 26 6 bits, this 26 bits into 26 bits. We need to make it into 32 bits. To do that, we need to perform the concatenation method, because we all know that in case of J-type instruction, for J-type instruction, we cannot use ALU. We cannot use any ALU. So how can we make this 26 bit into 32 bit? We need to perform a concatenation operation that would give us 32-bit memory address. Now, how can we do that? So, jump uses word address. That means our 32-bit address. Update program counter with concatenation of top 4 bits of old program counter value. For example, if the program counter value is, let's say, in hex, let's say in hex is 1 2 3 4 0 0 0 0. If the program counter value is this in hex, then the top or MSB 4 bit is this one, which is 0 0 0 1. This is the MSB 4 bit. Now 26 bit, we are getting it from this field, and then for word aligned we need to left shift it by 2. So this 26 bit and 2 bit left shifting, this two part gives us 28 bit. So we are left with 4 more bits. This is the 4 bits that we will concatenate with this 28 bits, and that would give us our desired 32-bit memory address in case of jump instruction execution. You can see in this data path that most of the data paths are not enabled. For example, register file, data memory, ALU, sign extension, even this part. None of these parts are enabled, because in case of jump we do not need any of this. So if I write a jump instruction, the jump is jump, let's say exit. This exit is going to be a 26-bit value. So to perform this jump instruction, we do not need a C. In this jump instruction, we do not have any register name or any memory address or anything. We just have 16-bit offset or address. Sorry, 26-bit offset or address. Now we need to make this 26-bit into 32 bits. We shall do it just by concatenation. So we do not need any arithmetic unit, any memory address, any memory data memory unit, or any register file. We just need instruction memory from where we would fetch this jump instruction. Program counter would give us the memory address of this jump instruction, and we'd fetch the jump instruction from the instruction memory. After fetching, this part works on generating the 32-bit memory address. So this is our instruction, which is 0 to 20. This is our 26 bits, and this is left shift by 2, which gives us 28 bits as it is given here. And then we have this 32-bit address just by concatenating the program counter. Sorry, not this one. Sorry, not this one. Not this one. uh, we perform the concatenation operation, and just by concatenation operation we get, see here it is written program counter 31 to 28 bit value of the program counter. So we just concatenate it and it goes to this multiplexer. So this multiplexer outputs this value. This is the value that is jump address 0 to 31 or 31 to 0. Okay, so this is how jump address gets calculated. So we should remember that in case of jump address, we do not need register file, we do not need ALU, we do not need any data memory. This is just this part performs the concatenation and generates the 32-bit jump address where the pointer should go and fetch the next instruction from. We have seen a general single cycle data path where three different types of instructions can be executed. In this slide, we'll see how we can design a data path which can only execute branch instruction. So our objective is to design a data path that is enough for branch instruction. We are not concerned about other instruction types or other instructions. We are just going to design a data path for accommodating a branch instruction. So let's write the instruction first. So the instruction is BNE, let's say 10, 11, and then else. So we all know this else is 16 bit, so we need to make it 32 bit. And this branch not equal to, that means ALU would compare the value of register 10 and register 11, and if they are not equal, then the branch instruction will be then the branch pointer would go to the branch target address. To design the data path, we all know the first component that we would need. We would need a program. We would need a program counter register that would give us the memory address of the instruction, memory address of the instruction, and then this memory address will go to the instruction memory. So this is instruction memory. Sorry, this is instruction memory. Instruction memory. This is program counter. These are program counter, and from the same value, the same value will go to the let make it bit bigger, a bit taller. So this same value will go to an adder for performing PC plus 4. So this link will generate will give a PC plus 4, and instruction from instruction memory. Next component is our register file. So this is our register file. So we will need to select two registers in the register file, and let's say we have a control unit here. So we have a control unit here, and from register file the value will go to the value of the register will go to ALU, and ALU would decide after performing the operation. ALU would identify whether they are equal or not equal, and based on their ALU's output, decision will be made. So to perform the subtraction, control unit would send ALU operation or ALU operation, what operation ALU needs to perform, and this and then so control unit also need control signal, and then we need to make this 16 bit into 32 bit. We can do this just by we need to perform sign extension and left shift by 2. This would give us 32 bit value. So this would give us 32 bit value. So this 32 bit value will go here, and this two will we shall perform an addition here. So this link would carry PC plus 4 plus branch offset. Okay. Now ALU output will ALU output will go to an OR gate. ALU output will go to an OR gate, and output of OR gate will go to an AND gate. Another output of the AND gate will come from the control unit, and then this we'll have a multiplexer here, and the value, this value will go here, and this value will go here, and then this is multiplexer selector port, and output of the multiplexer will go to the program counter. Now this is the diagram of of data path for this instruction. Now I shall give you the bit length of each instruction. This one would be 32 bits, and this one is 32 bit, and this is 16 bit value that is coming in. These two are 32 bits. This one is 32 bit, and the output is 1 bit, and this control unit generating BNE instruction signal, which is 1. So uh, this link carries PC plus 4, and this link already I already have said PC plus 4 plus branch offset. So let's say this is port 1 of the this one is port 1 of the multiplexer, and this is port, and this one is port 0 of the multiplexer. Okay, so let's say this is port 0 of the multiplexer. If this is the case, then what will happen is that so this is port 0 and this port 1 of the multiplexer. Now since this is a branch instruction, control unit would send branch enable control signal. So through this link, control unit will send 1. Now see what is happening inside the ALU. This link carries data coming from register 10, and this link carries data coming from register 11. If both the datas are equal, then their subtraction would be 0, which means 32-bit 0 will be output. Will be ALU will output 32-bit zeros. That 0 goes to this OR gate, so output would be 10. This was, since this one bit output, so this will be 0. And since this is branch instruction, so control unit generates enable signal, which is 1. So 1 and 0, the output is 0. So if the output of this AND gate is 0, this 0 is working as a selector for this multiplexer. So when this multiplexer gets 0, then 0 input gets outputted, which means this link gets PC plus 4. But if register 10 and register 11 are not equal, then the output of the subtraction that is performed by the ALU is anything in the range from this 1 to all ones, 32-bit values, and if that is feeded in this OR gate and the output is only 1 bit, then no matter whether the value is this or any other value in between this range, the output will be 1. So in that case, this one will be, in that case this one will be 1, and control unit already sending 1. So the output of the AND gate will be 1. So when the output is 1 and this works as selector for the multiplexer, so 1 will be selected. So this link will carry PC plus 4 plus branch offset. This is how branch target address it is calculated, and this data path executes branch equal to, and at the same time, if it is required, then it can execute sequential instruction at the same time. If it is not equal to, that means the execution is sequential execution. Performance issue. So we'll be discussing about the performance issue of a single cycle data path. So as it says that longest delay determines the clock period. So clock period is something like this. So this is our clock period, one clock period. So this is determined by the longest delay of the instruction. That means in our case, load is the longest instruction. It takes the longest amount of time. It goes to the instruction memory, then register file, ALU, data memory, and register a file again for performing the write back. Now, since this period is set as the clock cycle, so if any instruction is over around this time, so the remaining of the time, the remaining part is wasted. System does not do anything during this part, as in a single cycle data path, only one instruction can execute at any clock cycle. So unless and until the existing clock cycle is over, no new instruction can start executing. So not feasible to vary period for different instruction. This says that we cannot have variable clock period, and which means we need to fix the clock period, and this would result in waste of our time, and we are trying to achieve as much as we can from our system just to satisfy the ever increasing user need. So we cannot afford to have this kind of scenarios. Now, a volatile design principle, making the common case fast, will improve the performance by pipelining. So to improve this case, we shall be looking at more practical solution, which is called pipelining.